Log on, tune in, find out. Another good idea from Cambridge.
Good afternoon. I'm Valerian Toledano Laredo, from Northeastern, talking about stability conditions in Stokes vector.
Thank you very much. So I'd like to thank the organizers for inviting me to spend a month at the Newton Institute and to give this talk. It's always a pleasure to be in Cambridge. So what I'd like to talk about is joint work with Tom Bridgeland. And you can find it on the archive. And perhaps I should issue a small apology, similar to that of Eric Obdam's this morning, is that there will be some analysis in the talk, but very mild. But my only excuse is that I don't think it can really be got rid of. In fact, the statements will involve it. And so just to put you kind of in the mood, let me just remind you that I mean, since the work of Ringel, we know that quantum groups control the homological properties of the abelian category of representations of quivers. So Q is a Dynkin, finite Dynkin quiver. And said a little bit more precisely, this is the statement that UQ of, or maybe I should say UV of n is the whole algebra of this abelian category, which whole algebra is defined to be as a vector space. I mean, it's spanned by isomorphism classes of objects. Sorry, this is over a finite field. And then it has a multiplication, which is given by you multiply two isomorphism classes by summing over C's. And then you count the number of short exact sequences having C as middle term and A and B as side terms. And what I'd like to explain today is something that in some sense is in the spirit of that, namely that certain differential equations, so certain ODEs on P1 with values in N, that's the unipotent group with the algebra N, control in a certain sense wall crossing for moduli spaces of semi-stable objects in this category if you work over the complex number. So there's a lot of undefined terms here, but I'll define them when we come to it. This is just to give you a general idea of what I'd like to do. And the ODs I'm going to be looking at have irregular poles, meaning poles of order 2. And so they have so-called Stokes phenomena. And part of the point will be to show that these Stokes phenomena, which I'm now going to define, appear naturally when you start studying wall crossing for these moduli spaces. Okay, so that's the sort of the 5-minute trailer of the talk. So now I'm going to start talking about, I'm not going to assume you know about Stokes phenomena, so I'm going to define what Stokes phenomena are. Okay, so the setup is the following. I'm going to start with an algebraic group over the complex numbers. And even though we're using the letter G, which most of us think of as a semi-simple group, I'll warn you that G will not necessarily be semi-simple. Okay, because I will want to then apply whatever I'm going to talk about to unipotent matrices and maybe the Borel subgroups. Okay, and inside it, I'm going to choose a maximal torus. So just to set up notations, I'm going to decompose the Lie algebra of G as the Lie algebra of the torus plus the sum over the roots of these. Okay. And then I'm going to look at the following. I'm going to take a look at P, principal G bundle over P1, which is going to be holomorphically trivial. And I'm going to be thinking about a connection, a certain connection on P. And the connection is going to have the following form. Nabla is going to be equal to D minus Z over T squared plus F over T dt. Okay, so what kind of a connection is this? This is a connection which has a pole of order 2 at 0. That's the Z over T squared here. And I'm going to assume that Z is sort of regular semisimple, so lies in the Cartan, specifically on the complement of the root hyperplanes. Okay, so if you GLN, that means it has distinct eigenvalues. And then it has a pole of order 1 at infinity. The residue there is minus f, and I'm going to assume that this f is an almost general element in the Lie algebra, but specifically for just to make my life a little simpler, I'm going to assume that it's an off-diagonal element, meaning that it lives, so it has a zero projection on the Cartan. Okay, so that's the basic connection I'm going to be looking at. And now what do we want to do? We want to construct fundamental solutions of this connection. So we want to construct good fundamental solutions for this connection here. Okay. So let's start with a kind of little warm-up exercise. Assume I took f is equal to 0, then such a good fundamental solution would have the form e to the minus z over t. Okay, that would plainly be a fundamental solution of that connection there. Okay, what about f not equal to 0? Well, then you can prove the following. So we're going to look for solutions of the following form. So they're going to be like this, and then of course I'm going to put in something else. And in the first instance, I'm going to assume this to be just a formal solution. So a formal Taylor series in the variable t with values in my algebraic group. And I'm going to normalize it so that its value at the origin is equal to 1. Okay? And then it's a little result which you can easily prove at home, which says that such a formal y exists and is unique. Okay. And so far, the theory looks as it would look if you had a pole of order 1 at the origin. Namely, you would start by writing a fundamental solution which looks as good as it can, and then you would sort of solve for it iteratively, and you would prove, hopefully, that it has a unique solution. Now, the fact that the pole is of order higher than 1 has the following consequence, which is that, so problem, in general, the radius of convergence of f is equal to 0. So that's really the crack between regular and irregular singularities. Formal solutions don't generally converge. So what do you do? So then you look for something a little bit more modest. You look for something which is convergent on a smaller domain in the complex plane. So for that, let me just introduce, I need to introduce one notion, which is that of the Stokes rays. So the Stokes rays of this connection are the rays So what you do is you have your regular semi-simple element Z. You pair it against all the roots of your Lie algebra. So that gives you some points here. This is all sitting inside the T plane, okay, and maybe here. And then you simply draw the line, the rays from the origin to these points. So maybe. So this is not, you shouldn't be thinking of this as sitting inside the carton. This is not a root. This is not a root system. What you're looking at is just evaluation of all roots on a given fixed regular semi-simple element, and then the rays through it. Okay, and then another little piece of definition. Let me give it here. So that's really a notation. If I take a ray, then, so I'll draw it like that. Then I'm going to denote the open upper half plane that it determines, so the one which is orthogonal to it, by HR. Okay? Okay, and now the theorem is the following, is that if R is not a Stokes ray, then there exists a unique holomorphic fundamental solution YR from this half plane to your algebraic group G, such that YR times e to the z over t tends to 1 as t tends to 0 in each HR. Okay. So again, we can't be analytic around on the whole unit disk, but if we're willing to do things on half planes, and that these half planes are determined by almost all rays except these finitely many Stokes rays, then we can find solutions which are convergent and in fact are uniquely determined by that condition. Okay. And then, I mean, one shows, and in fact one can construct them, that they're actually asymptotic to the formal solution that we had there. Okay. So now we can define the Stokes data of this connection. And this goes as follows. Suppose I take two rays, neither of which are Stokes rays. Then each of them has a canonical fundamental solution, which is defined in a half plane. And so I can compare the two fundamental solutions, and then they will differ by a constant, which I'll denote by S, sigma, where sigma is this wedge, this acute wedge between the two rays. Okay, and that's a constant. That's a constant group element. Okay, it's a linear first order ODE, so obviously any two fundamental solutions differ by a constant. Okay, and now you can prove the following little proposition, which says, I mean, here, roughly speaking, that this constant lives in this wedge. And what this means precisely is, so what this means more precisely is that, first of all, this is unipotent. and its log lies in the sum of certain root spaces. And which root spaces are those? They are the ones for which the evaluation, well, what I was calling earlier alpha of z, now I'm calling it z of alpha. But anyway, the evaluation of the root on the regular semisimple element lands in sigma. Okay, so let's see what consequences this this little spectral lemma has. So corollary. Well, first of all, if sigma contains no Stokes rays, in other words, if no roots lie in sigma, then this constant is equal to 1, clearly, right? And then, second, if sigma contains only one Stokes ray, let's call it L, then S sigma, which I'm now going to rename SL, is the exponential of some element epsilon L, which lives on the ray, specifically again, like that, okay? And I'm going to call this SL a Stokes factor. Okay. And of course, so small sectors, those containing no rays, are irrelevant. You associate to them the constant 1. Those which are small enough that they contain just one ray, you associate them an interesting constant, which you call a Stokes factor. And of course, more general sectors, well, you can just decompose them as a product of things like that. And of course, the constant is going to be the product of the constants. So these clearly determine all these breaks in the asymptotics. And now the claim is that these Stokes factors are the good notion of monodromy for a connection of the form that we've been looking at. Specifically, you have the following. So the Stokes factors SL uniquely determine the gauge equivalence class of this connection here, okay? Which would not be the case if you just remember the monodromy around the irregular pole. All right. Now, let me tell you a little bit.
There's a question. So
yeah.
we normally use gauge equivalence when f is a function, but not just a quantity, right?
Right. Yeah. So here I'm I'm streamlining the presentation a little bit. You're right. What I'm doing is actually completely local theory. So you're absolutely right. In principle, the connection doesn't have to live on P1. It just has to live on the disk around the origin. Right. And F could have a tail, as you say. So for reasons that are maybe will become a little bit more apparent later on, I am just restricting to this case. But this statement is true for... No, right. Gauge equivalence on the disk. You're right.
And f is, from now on, f will be a function.
No. From now on, f will be a constant. Otherwise, I would have started with a function. Yes. No, but good point. But like I said, I'm trying to restrict to that case. Okay. All right. So another system of invariance, then I'd like to briefly describe. Okay. So another thing I could think of doing is the following. I draw a ray, which is not a Stokes ray, and I go all the way opposite, and I draw the minus the ray, and I'm assuming that neither one nor the other is a Stokes ray. And now I have two solutions. I have the solution that's, so YR, which you remember is defined on this half plane, and the solution Y minus R, which is defined on the opposite half plane. So here, they are defined on domains which actually do not overlap. Still, I'd like to compare them And I can do that in two ways. I can take my solution, which is defined here and analytically continued here, but I can do that up or down. And I will denote these two results by r comma plus or minus. Okay? And depending on what I do, I will certainly get a constant like this. Okay. So I start here, I continue up or down, and I find the solution which is defined here, the canonical one there, times a constant. And these things I will call Stokes multipliers. Sometimes I will slip and I will say matrices. And now you can readily convince yourself that the Stokes multiplier S plus, which you find again by continuing in the upper half plane there, you can do that analytic continuation in stages. And so this is a clockwise product of the Stokes factors. And likewise, S minus is equal to a clockwise product L in the opposite half plane of SL inverse. Again, just because. So you can go from factors to matrix to Stokes multipliers, and these are the relations that do it. But of course, you can always go back. And this is the reason is that these things plainly live in unipotent groups because of that spectral lemma that I discussed before. And once you have a unipotent group, you're trying to write it as a product of root, so to speak, one parameter root groups ordered in a set way. And of course, you can always do that uniquely. And so that gives you this arrow. All right, so okay, so far, this is a very classical theory due to Bolzer, Jurkat, and Lutz for G is equal to GLN, and all of this was generalized by Phil Bolch for G reductive. But actually, once you have it for GLN, you can also argue by Tanaka duality, and you actually get it for any algebraic group. Okay, and now let me tell you just a slightly more recent piece, which is the sort of isomonodromy problem for these connections. So how does the problem go? Well, now instead of a connection, we're going to look at a family of such connections. So I'm going to look at a family like this, and I'm going to ask the question, as Z varies, say in a little ball in this regular carton, how should F vary so that the monodromy, which we now understand to be the Stokes data, remains constant. Okay. So you're probably maybe more familiar with the so-called Schlesinger equations, which arise when you look at a similar problem, except that it's in the Fuchsian picture. So you have P1 with n points. You have a connection which is Fuchsian at all of these points. And then you start moving the poles, and you ask yourself, how should I move the residue so that the monodromy doesn't change? This is the analogous problem. And in fact, for GLN, these two are related by Fourier-Laplace duality. Okay, and now we have a precise answer to this question. So we have the following theorem due to Miwa, Jimbo, and Ueno for GLN. And this was adapted by Bolch for G reductive. But the proof, I mean, just the proof of GLN actually carries over also to the case of an algebraic group. And it says that the following are equivalent as z varies. Okay. So the first is easier to say, is that the Stokes factors do not change. Okay. You remember those are defined with respect to array. So here it's really just a local variation of z. You see that if I have my Stokes rays here, I vary z a little bit, I can always make sure that r doesn't cross any of them for a small variation. So this statement makes sense. Okay. The second is a statement that the Stokes factors don't change. Now you have to be a little bit careful how you formulate this. So the way you do it is that for any acute sector such that its boundary does not encounter the rays as they move when you move z, then you ask that the product, the constant S sigma, is constant in z. So the point is, there's a small subtlety, and maybe I shouldn't belabor it, but you remember the Stokes rays could have possibly more than one root lying on them, and even generically in Z, you could imagine this Stokes ray breaking up into two. So it doesn't quite make sense to say that a given Stokes factor is constant. You have to formulate it like this. Okay. And third, F satisfies. So you can write all that in terms of very nice nonlinear partial differential equation satisfied by F, which is the analog of the Schlesinger equation. And the differential equation is df alpha is equal to 1/2 sum beta plus gamma is equal to alpha of f beta f gamma times d log beta over gamma. Okay, so again, f alpha is I'm thinking of as a function from h reg as a locally defined function to the root space g alpha. Okay, and I'm saying that the exterior derivative of that is a sum over all pairs of roots which sum to alpha of that commutator f beta f gamma times d log of beta over gamma. All right. So that's pretty much what I wanted to say about Stokes data. So we've defined Stokes data. We know that now they're a good substitute for monodromy for these irregular connections. And we also know how to make sure for the connections of that form there, how to make sure that the monodromy doesn't change when I vary the most irregular parameter. Okay, so now let me just leave that aside. Let me jump and let me talk about wall crossing. In an abelian category. So the abelian category I'm going to choose is the representations of a finite dimensional algebra. So I'd like to work with coherent sheaves, say over a smooth projected curve, but I need a bit more finiteness properties, and these are certainly satisfied by such an abelian category. So I'll stick to that. And then I will need to do wall crossing. I will need a stability condition on A. So I will need a way to decide which objects in this category are stable and which are not. So this is a definition due to Tom Bridgeland. So by definition, a stability condition will be a homomorphism from the K group of A to the complex numbers, such that when you take an actual class here, you map to the upper half plane. And with such a stability condition, you can define the slope of an object as you would for vector bundles on a curve. So let's define the phase or slope of an object. If I take an object m, I will define it as 1 over pi times the argument of Zm. So Zm is a complex number in the upper half plane, so that's the arg of Zm is defined. This is going to be a number from 0 to 1. And now that I have a notion of slope, I can define semi-stability. So I will say that M is semi-stable if, for any subobject M, the slope or phase of n is less than or equal to that of n. Okay, so let's do maybe a small example. So let's take the representations of the A2 quiver. So the K group here is generated by the simple, so that's just 2 copies of Z. So a stability condition is just the data of 2 numbers in the upper half plane. In other words, if I so this actually prescribes a stability condition on this category. Okay, and now let's look at another object which is a non-trivial extension of one by the other, namely. So let's see, S2 E S1 0. Okay, this is the object with dimension vector 1 1 1. Then because the Z is additive on short exact sequences, the Z of this object falls here. Okay. And now I see that E has a subobject, namely S2, and its unique subobject, and its phase is to the right of that of E. Therefore, in this case, E is semi-stable. Okay. On the other hand, if I had started with the opposite diagram, namely if I had put Z of S2 here and say Z of S1 here, then clearly Z of E would have been somewhere here, and now I would have observed the opposite, which is that E has a subobject, namely S2, which is ahead of E, and so in this case, E is not semi-stable. Okay, and so here, I mean, this is what one calls wall crossing. And so a little bit more generally, what we want to do is so we're going to start by fixing a class in the K group. So if you were working with vector bundles, that would mean fix some churn data and look at, in the first instance, a set of isomorphism classes of objects in your category, which are of that class in the K group and are also semi-stable. So for the case we're looking at, this is general, this is a projective scheme. You can obtain it by GIT as King showed, and so it's a projective scheme. And what we want to look at is ask the question, how does this object jump as Z varies? So here we've seen it, the simplest instance of such a jump, this set was a 1 point here, and then it went from that to the empty set. Okay. Now there's a very beautiful algebraic approach to wall crossing. Which, as I understand, was started by Marcus Reinecke and then developed a fair amount by Dominic Joyce and maybe Kontsevich and Soiberman in the motivic setting, and it's the following. So we look first of all, we look at the moduli. We're going to look at first the moduli of absolutely all representations. Okay, so that's a moduli space. Technically, this is a stack of all isomorphism classes of objects in A. Okay. So what this is, I mean, again, in this case, it's a fairly gentle stack. So this is a sum. Sorry, it's not a direct sum. It's a disjoint union over all possible dimension of the stack of representations of that given dimension. And such a thing is simply the quotient of an affine variety which parametrizes all actions of my algebra over the d-dimensional vector space. My algebra has a finite number of generators, finitely many relations, so that defines an affine variety. And then I take the quotient by GLD of C. Okay? So that's a stack of all representations. And then I'm going to introduce delta alpha is going to be the characteristic function of the set I was interested in inside M. So this is just the delta function supported on this. And so you can ask, what kind of a function is this? Well, this is a constructible function on M. And it's interesting and useful to look at it inside the so-called whole algebra of A, which is, in the first instance, the vector space of all constructible functions. So by constructible function here, I'm going to mean a constructible function on this affine variety, which is invariant for the group GLD. Okay, maybe I can continue here. All right. So okay, and so this is an algebra. So there's a convolution product on this algebra, which is given as follows. So I take two functions. So I'm thinking of this as the algebra of functions on isomorphism classes of objects. So I take two such functions. I take an object, and I'm trying to define what the value of this is on M. And this is an integral of f of n g of M over n d chi. So this is an integral in the Euler characteristic sense over all subobjects of M. So if I were working over a finite field, this would literally be just counting subobjects of M. Here I'm working over the complex number, so I'm taking the variety of these subobjects and I'm then pushing it forward by Euler characteristic. Okay, so this is an associative multiplication. And little exercise, the unit is the function which I'll call 1, 0, which is just the characteristic function of the 0 object. All right. So example, say due originally to Ringo over a finite field, and then reworked over the complex numbers by several people. So Rietman, Schofield, and I think Kapranov and Vassereau. And so the order is random. I don't know who did what first. So just Ringo did things first for a finite field, and then after that I don't know. So I apologize. So the example is if you take Q a finite Dinking quiver, then the whole algebra comes out to be the universal enveloping algebra. So to it corresponds a semi-simple Lie algebra with triangular decomposition like that. And the whole algebra turns out to be exactly the enveloping algebra of n plus. Okay. In general, this whole algebra is a fairly sizable object because objects in the category can have moduli, and so the delta functions at each point in the moduli space are elements in the whole algebra. So in general, one finds a suitable subalgebra, which in some good cases one calls the composition algebra, and then proves that C is also the enveloping algebra of a Lie algebra, where n, it's a set of primitive elements. One is using here Milner-Moore, and it's just a set of f in C, such that f is supported on indecomposable elements, which happens to be the set of primitive elements here. So I'm not telling you the definition of C. It's not very difficult, but I don't want to. All right. Now, I want to illustrate one instance in which this product is really, because I haven't really justified why one would want to use the product so far, but want to illustrate one instance where this product is really manifestly very relevant, very useful. And this is to do with so-called harder Narasimhan filtrations. So which is an abstraction of the well-known fact for vector bundles. In other words, I take an object E, and then the claim is that there exists a unique filtration ending at E. So this is such that, first of all, the factors Fi is equal to Ei over Ei minus 1 are semi-stable. And then their phases are strictly decreasing. Okay, that's a little lemma, which is not very difficult to prove. And this is the following very beautiful rewriting. So rewriting due to, again, Reinecke. So I'm going to introduce the following. So SL for L array. This is going to be the sum. So it's going to be a generating function of all these delta functions. And what I'm summing over is I'm summing over array, meaning that I'm taking the characteristic function of all semi-stable objects such that when I evaluate Z on their class in K theory, I land exactly on this ray. So what I'm doing is just I had these things with their definition was clear, and I'm repackaging them in a slightly more compact way. I'm arranging them ray by ray. Okay. And then I have another notation, which is going to be 1a, and this is going to be the function that's equal to 1 for every m. Okay, that's a very boring element in the whole algebra, but it's there. And this is not the unit. You remember the unit was the characteristic function of the zero object alone. Okay, so now the proposition due to Reinecke is that the Harder-Narasimhan property implies that if I take something we've seen before in a different world, so I take now all my characteristic function of ray semi-stable objects, and I arrange them in a clockwise way, and I take this product like so, and I claim that this is equal to the boring function, which is equal to 1 over any object. Okay, and I'm going to leave this as a little exercise. This is nothing but you just spell out what this product is and use the fact that any object has a unique Harder-Narasimhan filtration. Okay. And then Reinecke and also Joyce use this to obtain wall-crossing formulae, specifically formulas that say that those delta functions for a given stability condition Z can be obtained as an explicit function, which I won't have time to spell out for you, of the delta functions for all other charges for different stability conditions Z prime. The main point here is that you read this identity as this being a function of those, but you can actually invert this identity. That's what Reinecke did. And so you can express this as a function of that. And so you read like this and like that. And so that jumps from one stability condition to the other. Okay. So I don't have time to explain this in detail. But you can push this to understand really, I mean, this wall crossing in gory detail, and in particular understand exactly where the discontinuities of these functions delta Z, delta alpha, which I view as functions from the space of all stability conditions to this Ringgold Hall algebra. So where does discontinuities lie? Now, then Dominic Joyce had the following idea, which is that he wanted to arrange, so these functions are piecewise constant. So you remember in our quiver example, they did not move for a while. They were literally constant. And then when you had two rays overlapping, all of a sudden there was a discontinuous jump. So what Joyce did is the following. So he formed a generating function for all of these objects, which is the following monster, if you see it for the first time. So you form a sum over all n, a sum over all ways to decompose alpha into n elements in the K group. So this is an element in the K group. Okay. And then you take delta alpha 1. So you convolve these things here. And then you weight that with where here for now, Jn are some ansatz weight functions. Yes, absolutely. Yes, yeah. So in particular, it's a finite sum, right? So it's a finite sum. So there's no question about convergence of that. What there is a question about, and this is the main desideratum of Joyce's construction, was he would like to say to the right-hand side is piecewise constant. So it has a lot of jumps. Now the question was, can you cook up some suitable functions, Jn, scalar valued functions, which will exactly cancel the discontinuities of the delta? Okay, so as to obtain something on the left-hand side, which is a continuous function of Z. So this is what Joyce did. So there exists some holomorphic, some Jn's, which are holomorphic with cuts, such that the corresponding F alpha, which I view as a function on the set of all stability conditions to this whole algebra, is continuous and, in fact, holomorphic. So by a very careful analysis of the discontinuities of those convolution products, Joyce manage to cancel them exactly using scalar valued correction factors. Then the second claim is that these JNs are unique. Okay. And in particular, that's the important thing, independent of the abelian category. In other words, they're completely independent of the algebra you take. And third, then Joyce observes that with those unique functions at hand, this F alpha satisfies a nonlinear partial differential equation, which is this differential equation here, which in this context fell absolutely from the sky. I mean, it's just an observation that he computes. These functions are complicated, but they're fairly explicit, and then he computes, they're defined recursively, and he computes, and then he shows that you get this differential equation. And I guess the idea of packaging things like this was motivated by quantum cohomology. So this is supposed to be a sort of, I mean, Joyce thinks of this as a sort of Gromov-Witten prepotential. All right, so now I'd like to say, so Tom and I were trying to understand, or like, what the meaning of this construction was. I mean, these functions are unique, so that means they have some canonical something to them. But why are they there, and how can we understand this construction? And so I'm going to reinterpret this construction in the following way. Actually, since we're in the UK, this is probably better written as like this. So you remember that I had this whole algebra, and inside I had this composition algebra, which was the universal enveloping algebra of some Lie algebra. And this Lie algebra is graded by the positive cone in the K group, so it's actually a pro-nilpotent Lie algebra. Okay. And I'm going to look at the corresponding pro-unipotent group. Okay. And on it, I have acting the following. So I have a torus which acts on it, which is a torus that's dual to the K group. So that's just saying that this Lie algebra is graded by the K group. And I'm going to look at the pro-solvable group, which is going to be H semi-direct product with N. Okay. So if I were dealing with a finite type quiver, this would exactly be the Borel subgroup of the corresponding Lie group. All right, so and so now I'm going to look at the following. So I'm going to take P, the principal B bundle on P1. Okay. And I'm going to look at a connection on it, which is of the form of our favorite form. Like this. So basically you should say in a word, what am I trying to do? I'm trying to explain why a differential equation which we met before in the guise of isomonodromy reappears completely out of the blue in this context. And that's what we'll manage to do. So I'm going to look at a connection of this form where Z is a stability condition. And you remember this is a stability condition is in particular a homomorphism of the K group into the complex number with some positivity property, and this is nothing else but the Lie algebra of this torus. Okay? So this is a semi-simple element, if you will, and in fact it's regular because by definition it maps every root in the upper half plane, so in particular not to 0. And then f I'm going to choose to be in n, which is the sum of n and alpha. So it's an off-diagonal element. Okay. Okay, now the theorem is the following. So the following conditions are equivalent. So the first is to say that f, whose weight components I denote by f alpha, is given by Joyce's generating function. Okay, so this is the complicated claim. So it says you take these complicated generating functions, well, do something which seems even less natural, you know, tuck them into this connection. The other claim is a description of the very same connection in terms of global monodromy data. Specifically that the Stokes factor of this connection here, corresponding to Stokes factor, which I was calling SL, you remember, corresponding to a Stokes ray L, is what I was calling boldface L, specifically the characteristic function of all semi-stable objects with Z alpha in L. Okay, and third, even simpler, the Stokes multipliers of this connection nabla are, so there's two, and you remember they depend upon a choice of a ray, and here I'm going to choose the ray to be the positive real line. So there's a Stokes multiplier corresponding to this upper half plane, which is S plus and this S minus. And so the claim is that S plus is equal to this boring function, which was equal to 1 on every object, and S minus is equal to the unit. So the function which is 1 on the 0 object and 0 everywhere else. And maybe I'll finish here. So what this is saying is that a much simpler way of saying something like that, kind of much more economical way, is just to say, to describe this in terms of global monodromy data. So it just says, take the irregular connection of this form, whose Stokes factors, whose Stokes matrices are just the function 1a and the function 1, 0. And when either of these conditions hold, f is holomorphic in Z, which is something that certainly Joyce has proved. This just gives us more conceptual proof of it, and satisfies df alpha, I mean our good old differential equation, like this. Okay, so this then doesn't, why does this follow? It doesn't follow anymore from the property of the special functions J that you're using. But if you believe this, then you have a family of connections which are plainly isomonodromic. Why? Because the Stokes, if I think of it in the Stokes matrix picture, well, the Stokes matrices are 1a and 1, 0, and these are completely independent of the Z. And so this is clearly as I vary Z, this is clearly an isomonodromic family, and therefore it follows by the general theorem of Jimbo, Miwa, and Ueno I told you, that F has to satisfy that nonlinear PD in particular. All right, so it's 4:30, so I'll stop here.
Any questions? Doesn't seem to be the case. Let's thank the speaker again. Thanks very much.